Okay, so today we're going to start the analysis portion of these cells. So here is my Fiji. Once you have your Fiji open, you can go ahead and get started. You open up your first image, and then basically I'm going to make this a little bigger so you can see. I have selected my square tool right now, this square one, so that I can select squares. And basically what we want to do is we want to capture one cell at a time. So if there's a part of another cell, that's fine, but there should not be two cells in there. It should only be one full cell. So Control Shift D to duplicate. It's asking me about the name. The name's perfect. I press OK. So then I'm going to go ahead and go to File. Actually, I don't think I grabbed the leg. Let's make this a little taller. Okay, there we go. Control Shift D, enter. So I have my cell, and then I go to File, Save As, and this is the first cell that I'm getting from this picture. So I created a folder that says single cell ROIs. Those are regions of interest. So I'm going to keep the name because this is the first cell. You can see 5-1. That means that it's image 5 and it's the first cell. So save. And then I get rid of that. And then I'm going to go ahead and grab my next cell right here, Control Shift D, then go to File, Save As, TIFF, and then instead of 5-1, I'm just going to put a 2, get rid of this guy, and then I go get my next cell. I don't think I grabbed the whole leg. Let's go higher. Okay, I don't think I went far enough. You want the cell to be sort of in the middle. You don't want any part of the cell to be touching like a corner because we exclude edges down the line, and it just won't quantify the cell at all if you do that. So this is going to be -3, and you basically do this for all your images. You want to do this for every single cell that you find that is alone and not touching anything. So sometimes you can only get 2 or 3 cells in an image. Sometimes you can get like 10. So it just depends. So I always go to the bottom, click on that last one, and that'll remind me of where we are. So that was 3, now we're 4, and yeah. Okay, so I finished that image and I went ahead and closed it up. So now I'm going to the next image. And there we go. So then I'm going to start over. This cell, I don't think it's touching the other cell, so it should be fine. Control Shift D. Yeah, there looks to be a little space here. Hopefully it gets captured. So then File, Save As, TIFF. And because it's the first picture, we just leave the name as is. This is not a cell because there's no nuclei. This one seems to be touching that one. I'm not really seeing any other individual cells here, so I think we're done. Let me zoom in here. Yeah, it kind of looks like it's touching. Maybe it'll count it as alone. We'll see. Let's see here. Okay, so we'll go File, Save As, TIFF. We're just going to do -2. And then that's it. We can go ahead and close this image and move on to the next one. So this area of the dish was a lot more confluent. So we just have to be like a little bit more careful to grab cells that look like they're alone, like this one right here is alone. Okay, so then whenever you're done saving all of your pictures for your cells, you go ahead and open up an Excel sheet because we're about to start getting our data, our quantifiable data. We're about to extract it from those images. And so I'm organizing my document like this. Here I have a description on top. This is the average nuclear area fraction. So I have 3 experimental replicates. That's N1, N2, and N3. And I have 2 experimental conditions. So I have tip cells and I have failing cells. and I'm curious to see what the difference is in their nuclear area fractions. So I took a lot of cells and we're going to go ahead and quantify their area of the cytoplasm and then the area of the nucleus. And then we're going to get the fraction that the nucleus takes up, the ratio. And then we're going to go ahead and we'll probably do like, I think we have about 10 cells per experimental condition. So we'll take the average of that and put it inside of each N. And then we're going to go ahead and take the average of that. And then we're going to go ahead and do the standard deviation. And then we can proceed, once we have all of our numbers, we can proceed to downstream analysis. So we'll have to do an F test, and the F test is going to tell us if we should do which type of students t-test. So I'll just call it a t-test. Yeah, it'll either be type 2 or 3, I think. And so after that, we'll go ahead and have our p-values, and then that's it. Our analysis will be complete. Okay, so here I'm just organizing everything how I want it. So anything that's like a title or something, I want it to be in red so that it stands out. So over here is going to be the tip cells, and then I have the cell area, the nuclear area, and then I'll have this divided by that, and that'll give me the nuclear area fraction. So remember, this is going to be my N of 1. And then I'll go ahead and make that bold and I'll make it red. At some point, I'll make it red. And then I should have about 10 calculations here. And then I'll take the average of that and put that in here for my N of 1. And then, so this area down here for the Excel sheet is where I'm going to use to keep that. Okay, so now I'm about to extract the quantifiable data from the pictures. So I go to my folder that was labeled single cell ROIs, or regions of interest. Remember that any portion of the field of view image is called a region of interest. Any subsection that you take from a picture is a region of interest. So we're going to go ahead and take our first one and we're going to bring it up and we're going to go ahead and quantify this. Okay, so then once we have our image, the very first thing I do is Control-Shift-D to duplicate the image. And then this is the code that I already had optimized to measure the nuclear area fraction simultaneously. So here we're running the properties and we're basically saying that we're scaling the image. So we have 0.17 pixels. Oh, 1 second. Okay. So then 0.17 microns per pixel. And that's how we're able to quantify or get quantifiable data from these images. So we're going to run the enhanced contrast. We're doing the Otsu threshold. We're applying colors with the LUT. Otsu dark reset. Let's see. Okay. Despeckling. So that means that if there's like little dots of fluorescence, we're removing those. And we're doing that a few times because some of these images have a lot of dots. Then we're making the image binary, and this is what's going to help us analyze our particles. You can't use that function without having a binary image, and binary just means like black and white. It has to be either or. So we're analyzing the particles in terms of size, anything that is 10 to infinity, so 10 microns to infinity. And I believe that's area. We want to show the overlay masks, and we want to display, we want the display to exclude the edges, and then we want to summarize the overlay. Okay, so we're going to go ahead and do Control-Shift-R to run just the selected code. Okay, here we go. Was I not clicking on it? Okay, let me try again. Okay, Control Shift R. Okay, there we go. So it says convert stack to binary. I'm just going to keep the default settings and press OK. All right, so it basically did everything for us. If we go to our little Fiji thing down here, we can see what it did. So this is basically our segmented image. And oh, hold on, I don't really like this right here that I kept it because it's really small. Let me try this again. So I'm just gonna exit out of everything and I'm gonna include discard. So just gonna get rid of everything and then I'm gonna show you what I'm gonna do. So I feel like I had this at 15, the size, and then I changed it to 10, but I'm gonna keep it at 15 because otherwise it splits things up in a weird way. So let's go ahead and grab our photo again. Okay, we'll Control Shift D, we'll duplicate it, we'll press OK, and then we're going to go ahead and run our code. So here we go, we're going to run all of this, Control Shift R, we're going to press OK, and then here we go. Okay, so this is basically saying that this is the area of our cell. This is the area of our cell. And then this yellow is the area of our nucleus. So 1, I believe, is the plasma membrane, so like the whole cell area. And then number 3 is the nucleus. And then it calculated this little guy as number 2, but we're just going to delete that. We don't need it. That's not a cell with a nucleus. That's just like extra fluorescence that was quantified because the whole circle is here. Notice that this over here was not quantified, and that's because part of it is on the edge and we excluded edges. Then if you go over here, you can see that this is, well, it's showing 1 and 3. I wonder why. Let's see. Okay, so here's our results table. So we actually have like quite a few tables. We have a log that we don't need. We have this results table, which is one of the main ones that we need. So it'll take, like, if you look at number 1, that's number 1 right there. And I think that's, yeah, the whole cell because the area is 1,385 microns squared. And then in terms of circularity, it's 0.150. So you can see that it's not very circular. It's, and then for cells, we don't really expect them to be very circular. They usually stretch out. This is a beautiful cell, and it seems really healthy to me. And then for number 3, that's the nucleus. It's 271 microns squared. And then that extra little piece that is right there, that guy is 22 microns. And that makes sense because if you look at the size, it's so much smaller than the nucleus. So it makes sense that that's 22 and this one is 271. Yeah, and then they're also labeled, like this one says number 2. Okay, so now we go ahead and transfer these numbers. We just want the area. So I can't copy the whole thing. So 1385.1. We're not going to put decimal. We'll put 1 decimal point. So 1385.1 is what I'm going to take to our Excel sheet. So this is our first one. So we'll put like numbers right here. So this will be 1. And then this is our first cell. So 13. I already forgot. So 1385.1. Okay. And then the nuclear area was 271.0. Okay. And this table, you're going to have to go to File, Save As, and save it as a CSV. So you want to save it. You're going to turn in all of these tables to me because that's my way of ensuring that you didn't just write random numbers on this Excel file and then turn that in. I need your raw data. Just like when you are a scientist, if you publish, you need to have all of this raw tables and everything ready to go. This is your data. If anyone requests it, you need to be able to send it out. Okay. So for the nuclear area fraction, We want to know what percentage of the nucleus, or what percentage of the whole cell area is taken up by the nucleus. So you just divide, we go equals, and then I think you say this guy divided by this guy. And then I think that's it, enter. Yeah, so it should be like 19%. And then this has too many numbers out back, so we just go, I think we just, oh, let's go in this way. Oh, it's not working. Okay. Okay, so it's this guy right here. So it's this little button right here. So you just press that and then it'll tell you like how much do you want. So basically 0.20, so 20% for this cell, 20% of the area of the cell is taken up by the nucleus. Okay, so then we want to do 10 cells. We'd always do more, but I think for this class, we'll just do 10. But in general, the more you have, the better your data, the more accurate. Okay, so you go get your individual cell images, and then you bring it in there, and then you run this chunk of code, which the properties are to set the scale so that you can actually quantify. This is a 20x image, so it is 0.17 microns per pixel. So that's what I put in there. And then enhance contrast, auto threshold. So here we're using the Atsu. Then we are enhancing contrast again, and then we're turning that into a mask, which means we're just making it binary, or we're making it binary down here. We're despeckling, that gets rid of any dots that you might see in the background, and you can apply that function over and over again. And then we're finally analyzing our particles. So basically all we're doing here is cleaning, first of all, setting the scale and then cleaning up the image so that the cell and the nucleus look more prominent, where that they can be segmented and the background looks more black. And so after that, you can go ahead and analyze the particles, and we're doing a size of 15 microns squared to infinity. And so we're going to go ahead and put Control-Shift-R, and then we're going to press OK, and it's done everything for us. So we don't care about the summary. We're going to get rid of that. We're going to go look at our picture and look at how beautifully it segmented the cell area and also the nuclear area. If you go over here, you can just see the nucleus. But basically, these are the numbers that we want. So we go ahead and go to our results, and then we have our, let me show you this in big. So here's our Excel file, and this is how I organized it. So average nuclear area fraction. For me, I have tip cells and phalanx cells, and I have young cells and I have old cells. So I'm looking at the nuclear area fraction from young to old to see if they change. And we have an N of 1, 2, and 3. Then I get the average of that. Then you get the standard deviation. Then you perform an F test. And the F test will determine, it'll tell you if you need to do what kind of t-test. So if you need to do a type 2 t-test or a type 3 t-test. Once you're done getting all of your data, then you go ahead and get your p-values. So down here is where I've organized all of my stuff, and you guys are going to do the same, and I want you to do 10 images per sample. So here's my young, and it's going to be phalanx, N of 1, N of 2, and N of 3. And so I'm getting the cell area, the nuclear area, and then the nuclear area fraction. And then you just do that for all of them. So now my young tip cells, N of 1, N of 2, N of 3. So yeah, I'm filling out the N of 3 right now. So I'm just going to make this smaller down here. Okay, so the first thing you do is look at your picture to make sure that everything was segmented beautifully. You basically just want to see this perimeter of the cell, and you want to see the perimeter of the nucleus. Then you want to write down like the area. So right here, 1 was that larger one and 2 is the smaller circle. So 1 is the larger, 637.2 for the area. So 637.2. And then the nuclear area is 220.9. And then the nuclear area fraction, you can put your formula once and then you drag down. So it's basically this number divided by this number, and then you put equals, and that'll give you what you want. And then you go use this right here to make it to where it's only two places over. And that's it. We can actually keep going to the next cell. But what we're going to do is we're going to save this first. So you go to File, Save As. We want to save it as a JPEG. And then we're going to go into our folder. So this is where we have our single cell regions of interest, or ROIs. And then we're going to go ahead and save it into this folder. And we don't have to change the name. The name is the same as it was up here. Once we clicked on this, it kept the name. So we just hit save. And then we can get rid of this. And yeah, then we go ahead and save this. So File, Save As. And then we're gonna get the name from here, which is our last image. But we go into the results and analyze particles. And then we just put .csv because we want to save it as a CSV file. You also want to make sure to close all your windows. So we want to close our results table, and we want to close our region of interest manager. So this one I had trouble moving, so you can just like make it large, and then we get rid of it. And then you can also go down to your Fiji icon at the bottom, and it'll tell you everything that's open. So we basically don't need anything except for our code and our Fiji bar, and that's it. So everything else we went ahead and closed. Okay, so now we're going to check to make sure that our CSV file saved correctly. We want to make sure that it comes up, and that's perfect. So here we have the area, which is what we want, and we see that like it actually saved. It has the name of the image, and it saved our results table as a CSV file. You guys are going to be submitting that to me as a part of your homework assignment. So then we go to our next image. There we go. So then we go to our coding, Control-Shift-R, enter. We get rid of the summary. Let's go ahead and look at our picture. This is perfect. There could be other stuff here, and it doesn't matter because you really only care about what is surrounded by yellow. And then we go look, and our area is 652. So we go here, and we have 652.1. And the nucleus is 229.1. And for the nuclear area fraction, we just go like this. Oh, it's 35% exactly? Okay. Okay, so I'm saving everything for that second one. Remember to do .csv, save, and then we're done. Okay, then we go grab our next cell. That one looks beautiful. And then Control-Shift-R, enter. And this one looks a little bit more messy. Let's get rid of our summary table. Okay, but it doesn't matter. So you can see that there's a lot of white here. And that's perfectly okay because our cell looks like it was really well segmented. So let's go ahead and check this out. Ooh, that's a large cell. It's 819.2 microns squared, and then the nucleus is 241.8 microns squared, and then we just go ahead and bring that down, and this is 30% nuclear area fraction. Okay, so now I'm encountering a picture or a cell where it doesn't actually want to work. Like, we'll get rid of the summary. If you can see here, there's only in the results table, there's only the area of one item, so just like the cell, but it didn't give me the nucleus. So for this one, I'm going to go ahead and get rid of all of this. Don't save. Okay, so then I'm just going to go down here. Which one was it? This one, I think. Okay. So yeah, I'm going to go to images, stacks. Actually, I could have left the other area, stacks to images, and then I'm going to go ahead and I think I can run the code for like each of these. So I'll run the code here. Boom. Control Shift R. The product of channels 2 slices 1. Okay. So channels, I guess I have to do channels 1. Okay, let's see if that works. Okay, Control Shift R. Okay, that worked. So we got the area for the cell, and then now we want to go down to our like whatever down below to the Fiji icon, because we want to find our nucleus. And now we're going to go ahead and run the same code for the nucleus. So Control Shift R, and then we'll go look at the nucleus. Perfect. Okay, so we got the nuclear area and we got this area. So we're just going to save the images, both images. One of them is just going to be labeled the same, but it'll be like cell, and the other one will be like nuclear. But all we were looking for was not the summary. Let me see. The results. So we've got our cell area at 514 and our nuclear area at 157. So yeah, I'll show you how to save these. We go to File, Save As, JPEG. And so we're going to keep the same name. But we're going to say cell, because that's like the whole cell. Save. And then we're going to go here and we're going to say File, Save As, JPEG. And we're going to keep the same name, but we're going to say underscore nucleus. Boom. So now they're labeled the same. We can go ahead and get rid of them. We can get rid of our ROI, and now we can go ahead and save just one of these with the name of the cell. So save as, and then we go grab one of those. Okay, I should have left them open because now I forgot the name. Okay, right here. P5N2. So P5N2, this was an N2, and it was like 6 something. So was it this guy? Oh, I think it was this guy. Okay. And then we could just remove like all this and just leave the name. And we'll put save. Oh crap, I saved it in the wrong place. File, save as. Okay, let's go grab. It was this Excel file. We'll delete it from there, but we'll save it where it actually belongs, right here. Okay, and we can go delete it from the other place later, because a CSV file doesn't belong there. But basically, that's how we did it. We were able to get everything we needed, like all the numbers, even though it didn't want to work together. But don't forget to go ahead and change your channels to 2 so that the rest of your code works on the rest of your images. Okay, so I just finished all of my samples. So here we have young, and this was supposed to say, oh yeah, young phalanx cells, and then young tip cells. So in the first column is a cell area, the second column is the nuclear area, and then we have our nuclear area fractions. So what we're going to do is we're going to go ahead and fill in this top part of the table right now. We're not going to worry about the old stuff yet because I have to go back and redo all this, and it takes a few hours. So for the young tip, I have to get the average of my n equals 1. So here's my n equals 1, and we're talking about nuclear area fractions. So that's what we're talking about, average. We can do averages of everything. though, just to create like different types of graphs. So this one will be the cell area average. So you just go equals average, you double click on that average, and then you just highlight. Okay, so here I have 12. That's fine. I know, actually I want, yeah, that's fine. Okay, so then enter. So that's my average for this column. So I'm just gonna put in bold and caps lock and bold. Okay, I'm just gonna say average. And then so I'm doing the same thing here. So I'm just gonna go like this. And everything has been filled in for me. So the only thing that I forgot to do here is that I wanted it to just be like, I think for averages, Kara doesn't like, she just wants whole numbers. So we're going to go ahead and do that. So it looks like for my phalanx, N of 1, my average cell area was 810 microns squared. My average nuclear area was 235 microns squared. And then my average nuclear area fraction was 0.33 or 33%. So we're going to go ahead and do the same thing over here, control copy. So for the rest of my samples, I have 10, but I'm going to go in, like, for your class, I only expect 10 from each of you, but for myself, I'm actually going to go in and add a lot more. I'm probably going to be doing at least 20 per sample. But here we'll go ahead and do the same thing. We'll make the formula again, equals average, double click, highlight from number 1 all the way down here, then close the parenthesis and hit enter. Okay, there are one or more circular references where your formula. Okay, let's try that again. Equals average, average from here down to here. Close that, enter. Yeah, okay, it works now. So my average here was 516. We're gonna go ahead and bring that out. Okay, to here. So yeah, 516, that's a lot lower than the first one, so that's strange. The nuclear size is 235, over here it's 189. So that's why the more samples that you have, the more accurate that you are, because most of the time for your N1, N2, and N3, you actually want the numbers to be like more close. Okay, and then here I forgot to do this thing again, where we just have whole numbers. And there we go. Oops, 40%. So here's 33%, over here is 40%. And then we'll try it over here. Okay, I did notice something. So if I put my average here and then I do like the whole like number thing, where I remove these places, when I go out, it'll give me a 0 over here. So first, go ahead and do that. And then go ahead and do the whole number thing. Like that. Because that way you will actually get the correct values there. Okay, so now I'm done getting all of my averages down here. So the next thing I'm going to do is go ahead and write them in for my N1, N2, and N3. So pay attention because I wrote tip first and then phalanx, but over here I start with phalanx first. So 810 is my, oh wait, no. So we're doing the nuclear area fraction here. So that's going to be this guy, so 0.33. So phalanx N1 is 0.33. Phalanx N2 is 0.40 for the nuclear area fraction, so 0.40. And then my N3 for phalanx is 0.42. 0.42. Okay. And then for tip, it's going to be 0.38, 0.29, and 0.4. So 0.38, 0.38, 0. Was it 29? 0.38, 0.29, and 0.4. 0.29 and 0.4. Okay. So then my average would just be equals average of these guys. Okay. And then we'll go ahead and do that thing. Oh, wrong way. Okay. And then we do the same thing down here. So it already took these averages, so it's 0.38. Standard deviation, we just do equals STDV. Standard deviation, it's this one, the one that's like normal, STDEV. Okay, and then we just grab the first three, the N1, N2, and N3, enter, okay. And then the same thing down here, but I don't know if it'll just bring it down. I guess it does. Okay. So for my standard deviation, I will also get rid of some of those decimals. Okay. Okay, so now we're going to go ahead and run the t-test. We have our standard deviations, our averages, and everything, so we're going to go equals t-test. Instead of double-clicking here, I like to go to the fx right here, double-click there. Oh, something happened. That's not what I normally. Let's try it again. So t-test, we're going to go, I guess we'll double-click here, but then I go to the f of x. Okay, that's perfect. So for array 1, you're just going to get those N1, N2, and 3. You highlight them, then you go to array 2, and you highlight N1, N2, and 3 for phalanx. Tails is going to be two-tailed because it can go in any direction. And then the type of t-test is going, it tells you right here. Type is the kind of t-test. Paired is equal to 1. So a paired t-test would be like, the example that I saw was like the population in Africa in 2000 versus the population in Africa in 2010. So it was the same place, the same location, and you're just looking at the population at 2 different years, 10 years apart. So that's a paired t-test. Now, 2 sample equal variances. So when you have 2 different samples, which is what we have, and you have equal variance, that's a type 2 test. Now, if you have unequal variance, then that's a type 3 test. So I ran an F test, but also there's like a normal rule where if the variance, one variance, the higher variance divided by the lower variance is equal to less than 4, then that means that it's equal variance. And if it's higher than 4, then it would be unequal variance. So if it's less than 4, then it'll be type 2 test for equal variance. So we're going to say, oh, I don't think I put type 2 right there. Okay, cool. So then enter, okay, type 2, okay. And then it gave me 0.57. So the difference here was not statistically significant because it has to be 0.5 or less. But this was more than 0.5 because it would be 0.50, but instead it's 0.57. So if we end up doing more than 10 samples, we'll probably get statistically significant results. But here it's showing that the nuclear area fractions are different, and they're so different that they were almost statistically significant. But here they're not they barely missed the mark. Okay, so then I just copied and pasted all that, and now we're doing average cell area. So I went ahead and brought in the N1, N2, and 3 for the average cell area. And now I'm going to go ahead and do the t-test. So equals t-test. So double click here, then click here. So our array 1 is this, and then array 2 is this. And then tails are 2 because it can go either way. You can have smaller or larger areas. And then we're going to assume equal variance again. So then here it's going to be a type 2 test, and we're going to press OK. And 0.35. Oh, over here we were far away. I misspoke because it's supposed to be 0.05 and then 0.5. That's really high. So we're not even close to statistical significance. And then here it's 0.3. So yeah, that's so basically what this is saying is that according to our limited data, it looks like the tip and phalanx, these two different cell types, they have pretty much the same nuclear area fractions. They have similar nuclear area fractions. And in terms of the average cell area, so like their size, they also have similar sizes. Their sizes are not statistically significantly different, so they have similar sizes. Okay, now we want to start creating our graphs. So then what we're going to do is we're going to put our two cell types right here. So tips versus phalanx, our averages, that's the average from the N1, N2, N3. We just took those. I copied and pasted those values here. And then our standard deviation, again, I copied and pasted those values here. To make the graph, we're just going to take this information and then we're going to go to charts and we're going to do the cluster to column. Make this smaller. Okay, so then here we go. You can just see so this is the average nuclear area fraction. So you can see that for tip cells, it was about 0.35, and then for phalanx, it was about 0.38. The values are really close to each other. And then here, Kara doesn't like this, but when I pasted them over, it like removes whatever I had done. So we have to like go back and redo that. But there we go. And then it fixes it, anything you do there. So then another thing we do is you go to the little plus sign, and then you're going to remove the grid lines. We're going to go ahead and add error bars. We're going to add axis titles. And yeah, so this title is going to be the nuclear area fraction. And then here is going to be cell type. And then that's that there. And then, axis title right here. So this will be, it's unitless. It's just nuclear area fraction. Okay. And then we get rid of this, and then this is looking better now. And then anytime in Excel that you add your error bars, these are actually incorrect. So in order to make them correct, you have to go and use your standard deviation. So that's why I brought those values along. You right click and you go to format error bars. And so in Mac, this is going to be different. You have to Google how to do this, but basically you you right click on the error bar and then you click custom and then you go to specify a value. So for positive, for this one actually, you just select like the 1 bar, I think, that, and then you do the same thing here. Or actually, I think you pick them both. Custom error bars. Yeah, I think it's all the bars. Yeah, they're both selected. Okay, so then you just basically select both of them, and then you go to the negative and you select both of them again, and then you press OK. And now the bars are accurate. So these are accurate, and it had to change the graph. Before it wasn't starting at 0, and now it is, but this is actually really accurate, and you can just see how close the nuclear area fractions are from tip cells to phalanx cells. And the fact that we have an error bar here tells everyone that we had a N of 3, so we had 3 experimental samples at least. Okay, so now I just pasted the next graph over the average values, and then it's because I used a formula for the average, it's coming this way, so I'm going to put Control Z so you guys can see what to do. Let me get rid of this whole thing. Okay, I'm pasting the values again. So paste, Control V. So we're gonna go to paste values right here and numbers formatting. Okay, so I pasted the values and the formatting as well. So we're gonna do the same thing with standard deviation. We're gonna grab that, Control copy, and then we're gonna put it right here, Control V. And then again, we're going to go here, paste values and number formatting A. Okay, perfect. So last time for my average, it didn't have any decimal. Wait, average was 0.36. Yeah, I'll remove the decimals. We'll go ahead and do that for everything. Okay, so we'll go ahead and make this graph now. So we'll just go here. We'll go charts, cluster to column. And again, we can see how similar these values are. So this is like area, average area. Okay, so now I'm just fixing this graph exactly like I did the other one. So I'm doing the average cell area, and so you have to put the units on this guy. And so you go to insert, so it's area, it's going to be microns squared. So you go to insert symbols, symbol, and then you choose the micro insert, close, and then you add an M, so that's microns, and then the little caret, and then a 2, so that means squared. So those are the units that we're using. And then everything else is basically the same. So cell type. And then I went ahead and added the scale bars already. Those are the ones that are not accurate, so we're going to go ahead and make those accurate. Okay, so now we have two bars, or two graphs. They look similar. We have our nuclear area fraction and our average cell area. So now we're going to do our average nuclear area. Okay, I'm done. So now we have all three graphs. And remember, any types of images that you do, there's so much quantifiable data that you can extract, and then you can make the same types of graphs. So here we have this is not the nuclear area, it's the cell area. Cellular, wait, oh God, I hate Excel. Once you learn how to code really well, you'll be able to do this in R. You'll be able to make all of your graphs and everything in R. Where? Okay, we're back. So this is it is the nuclear area fraction. Okay, so we see here from 0 to 50, we've got the tip cells, the phalanx cells, and we know that our error bars are accurate. Then we have the average cell area from 0 to 1200 microns squared, and you can see that our error bars are accurate. The tip cells had a lot of variability. It looks like we went from like 400 to 1200. That's a huge range. And then the phalanx cells had a little bit less variability. They tend to be a little bit smaller in terms of their average cell area. And then for the average nuclear area, it's about the same size almost. The tip cell nucleus is a little bit larger in general than the phalanx, but not in a statistically significant manner because there's too much variability, as you can see by these large error bars. So that is why the more samples that we actually collect, so I would like to do at least 20 or 30 cells per condition. And I think that would definitely reduce our error bars a little bit. And then we might get statistical significance, at least in this one right here, for the average cell area, maybe. But yeah, that's how you do that.